This question was asked in the GATE Physics paper 2021. This is a numerical answer type question having 1 mark. The topic of the question is quantum statistics. Specifically, this question was asked from the chapter Blackbody Radiation. The question is, a light source having its intensity peak at the wavelength 289.8 nanometer is calibrated as 10,000 Kelvin, which is the temperature of an equivalent blackbody radiation. Considering the same calibration, the temperature of the light source in Kelvin having its intensity peak at the wavelength 579.6 nanometer rounded off to the nearest integer is, so we have to find the value of the temperature at which the intensity peak is coming at 579.6 nanometer. Let's see how to solve this problem. Before going to the solution part for this question, we first quickly recapitulate the concept of blackbody radiation. Now, blackbody radiation follows the photon statistics or Bose-Einstein statistics with the chemical potential mu equals to 0. The number of photons having frequency range from nu to nu plus d nu is given by n as a function of nu times d nu equals to g as a function of nu d nu divided by exponential of h nu divided by kBt minus 1 per unit volume. Here, g as a function of nu is the density of states or dose of photon gas per unit volume, and that is given by 2 times 4 pi nu square divided by c cube. Here c is the speed of light in the vacuum. Now this factor 2 is coming due to the two state of polarization of photons. The energy per unit volume of the radiation field in the frequency range nu to nu plus d nu is u as a function of nu times d nu equals to h nu times n nu times d nu. So u as a function of nu times d nu equals to h nu times this quantity n as a function of nu d nu that we have shown in the previous slide, and that is given by g as a function of nu times d nu divided by exponential of h nu divided by kBt minus 1. So if we put the value of g as a function of nu, that is the density of states of photon gas, then we'll have the energy per unit volume of the radiation field is u as a function of nu d nu equals to 8 pi h by c cube times nu cube d nu divided by exponential of h nu divided by kBt minus 1. Now we'll change the variable frequency nu to the wavelength lambda, and lambda equals to c by nu. So we'll have u as a function of lambda times d lambda equals to 8 pi hc divided by lambda to the power 5 times d lambda divided by exponential of hc divided by lambda kBt minus 1. So we have the energy density for the radiation field per unit volume. U as a function of lambda is given by this expression. So this energy density is also known as spectral energy density. Now we'll consider two regimes of the wavelength lambda. For a small wavelength of the blackbody radiation, the exponential term here will be very greater than 1. So the spectral energy density can be approximated as 8 pi hc by lambda to the power 5 times exponential of minus hc by lambda kBt. So this is known as Wien's distribution law. The second scenario will be the wavelength of the blackbody radiation is large. For large lambda, the exponential term in the spectral energy density can be approximated as 1 plus Ch divided by lambda kBt. So if we put this approximated form of this exponential term, then we'll get u as a function of lambda as 8 pi kBt lambda to the power minus 4. This is known as Rayleigh-Jeans formula. So for the small lambda case, that is the Wien's distribution law, as lambda increases, our spectral energy density also increases. But for the Rayleigh-Jeans formula, that is for large lambda, as the lambda increases, the spectral energy density u as a function of lambda decreases. Now we will plot the spectral energy distribution of the blackbody radiation as a function of blackbody radiation wavelength lambda. So we will consider three temperatures such that T1 greater than T2 greater than T3. So we will plot the spectral energy density versus lambda for these three temperatures, and the plots will look like this. As we can see, as the temperature is increasing from T3 to T1, the intensity of the curve is getting increased. Now for the temperature T1, the peak of the curve is coming at wavelength lambda 1. For the temperature T2, the peak of the curve is coming at wavelength lambda m2. And for the temperature T3, the peak of the curve is coming at the wavelength lambda m3. We can see as we are going from lower temperature T3 to higher temperature T1, the peak value is getting blue shifted. That is, the peak wavelength is getting decreased. So this is known as blue shift. So for T1 greater than T2 greater than T3, we have lambda m1 less than lambda m2 less than lambda m3. Also, one important thing can be noticed here, that if we draw a curve passing through the peak of the u versus lambda curves, then it looks like a hyperbolic curve, that is shown here by the dotted line. So in the previous slide, we have seen how the energy spectral density of the blackbody radiation varies with the wavelength lambda, and the peak of the curve, that is u versus lambda curve, blue shifted as the temperature is increasing. Now we will discuss about an important concept, that is Wien's displacement law. So we have the spectral energy density u as a function of lambda equals to 8 pi hc divided by lambda to the power 5 times 1 by exponential of hc divided by lambda kBt minus 1. We will consider z equals to ch divided by kBt. So we can write this spectral energy density expression as u as a function of lambda equals to 8 pi hc times a function, that is f of z by lambda. Now this function f of z by lambda is defined as lambda to the power minus 5 times 1 by exponential of z by lambda minus 1. Now we want to find the maxima for this above distribution. For that, we will take the first derivative of this u and we will equate it to 0. So du d lambda will be 0. From here we can write df d lambda equals to 0, and this equation will give us 1 minus e to the power minus z by lambda equals to z by 5 lambda. So we cannot solve this equation directly. we have to solve it numerically to find the lambda max at particular temperature. So this equation will give the solution lambda max times T equals to Hc divided by 4.965 kb. Here kb is the Boltzmann constant. So if we just put the value of Planck's constant H and value of the c, that is speed of light, then we will get lambda max times T equals to 5.1 millimeter Kelvin. So if we notice that this is a hyperbolic equation. So it tells us that the maximum wavelength is varying with temperature inversely, and this relation is known as Wien's displacement law. Now coming to the solution part of our question. Let lambda mi denote the wavelength at which the intensity of emitted radiation is maximum for a blackbody radiation at temperature Ti. According to the Wien's displacement law, lambda mi times Ti equals to constant. So lambda mi will be inversely proportional to the temperature of the blackbody radiation Ti. According to our question, lambda m1 equals to 289.8 nanometer. The temperature T1 is 10,000 Kelvin. Lambda m2 equals to 579.6 nanometer. So we have to find the corresponding temperature of the blackbody radiation T2. Now we will apply the Wien's displacement law, that is lambda mi proportional to 1 by Ti. So we can write lambda m1 divided by lambda m2 equals to T2 divided by T1. So T2 can be written as lambda m1 divided by lambda m2 times T1. Now in the question it is given that lambda m1 equals to 289.8, lambda m2 equals to 579.6 nanometer, T1 is given by 10,000 Kelvin. So if we divide 579.6 by 289.8, then we'll get 2 here in the denominator, and 2 will divide the 10,000. So effectively we will get the temperature of the blackbody radiation is 5000 Kelvin. So 5000 Kelvin is the correct answer for this question. According to our solution, the temperature of the light source in Kelvin having its intensity peak at the wavelength 579.6 nanometer rounded off to the nearest integer is 5000 Kelvin.